About the absorption and digestion mechanisms of individual macromolecules. So what it looks like for carbs, for proteins, and for fats. Now, we know digestion to be the breakdown of these larger macromolecules found in food, right? Such as carbohydrates, proteins, lipids. They need to be broken down into smaller monomers. Right? We talk about carbohydrates, and the monomers of carbohydrates are going to be monosaccharides. For proteins, that's going to be what structure? What are the building blocks of proteins?
Amino acids.
Amino acid. So digestion is the process of breaking those molecules down to their smallest components so that they can be absorbed. And then alternatively, absorption is the movement of those monomers across the epithelial membrane. Right? So moving that molecule from the external environment, which is the lumen of the gastrointestinal tract, remember that's still external, into the internal components, which is across into the capillaries, into the blood, into the cells. We're also going to speak about this absorption of vitamins, minerals, and then water. So this slide is just to remind us of the various types of transport. So on the top, this is a mechanism, active transport. So this would be what type of active transport on top. We're using ATP. What type of active transport is this? Primary, good. Primary active transport. And then on the bottom, what type of transport would this be? Where we use or harness the energy of another ion. Secondary active transport. Right? This is just to remind us of the various types of movement, types of transport, which we'll point out today. Let's start by looking at the absorption and digestion of carbohydrates. Now, carbohydrates are built from monosaccharides, and in order for carbs to be absorbed, they must be in that form. They must be in their smallest form, that monomer. So disaccharides and polysaccharides, which are much more complex carbs, must be digested or broken down into those smaller components. Digestion of starch, as you mentioned yesterday, takes place in the mouth, or starts in the mouth, rather, and that takes place under the influence of salivary amylase, right? That enzyme that's in our saliva that helps to start the breakdown of carbs. If you have food in your mouth, if you have starches in your mouth over an extended period of time, you'll notice they start to disintegrate, they start to break down, and you can taste them. Right? That's the salivary amylase affecting those carbs. There's also pancreatic amylase, which is found down further in the intestine, that's secreted by the pancreas. And both of these together help to break down these carbs into their smaller components. So let's look at the mechanism for the absorption of carbohydrates. Now we want to bear in mind that in order for, when we speak of absorption, we're speaking of movement from what area to what area. What's the direction of movement for absorption? From the lumen of the GI tract, across the epithelial cell, into the capillary bed, which is at the basolateral membrane, right? We want to bear that in mind. All right, so we have the lumen of the GI. This is where we have those complex carbs, or those monomers that have been broken down. And then we have the basolateral membrane, or the basolateral surface, and the apical surface. So this is our cell, our epithelial cell. Now, because this is an intestinal cell, we know we have our microvilli, okay, which is forming, what's the structure formed by microvilli in the intestines? The brush border, right, the brush border. We saw this in the proximal convoluted tubule, and again here in the intestinal enterocytes, okay? Now, in order for those monomers we talked about, those monosaccharides, to move across the epithelial layer, So this is an epithelial cell. Let's just make note of that. An epithelial cell in the intestines, there needs to be movement across the apical surface from the lumen into the cell, and then movement across the basolateral surface from the cell into the capillary bed. Okay. And so we have movement taking place at the apical surface, and we have movement across here. So let's talk about examples such as glucose and galactose. Now, we looked at this mechanism before. We talked about this exact mechanism before. This is secondary active transport. In order for glucose to enter the cell, it needs to harness the energy from another ion that's being moved, right? And so we have at the basolateral membrane, what's the pump at the basolateral membrane that's exchanging potassium and sodium? What do we call that pump? The sodium-potassium pump, right? So potassium is going in and sodium is going out, right? And that is using energy, ATP. So this is an ATP pump. But this creates a gradient now. So there's lots of sodium leaving the cell. And so we have a gradient where sodium wants to move from the lumen into the cell. Okay, so sodium is going to move across this transporter passively into the cell here. And as a result, what's going to happen next? Glucose or galactose is going to hitch a ride here, right? It's going to harness that energy that's released as sodium moves along its concentration gradient. We have some ATP being released, and that ATP is going to be harnessed by glucose or galactose and moved into the cell that way. All right, does that make sense? We talked about this similar mechanism before when we looked at the proximal convoluted tubule and how glucose was moved across that PCT cell. Righty? So the important take-home point here is that glucose moves into the cell, secondary active transport, because of the gradients that are being created. All right, let's continue on talking about how carbs behave, or proteins rather. Let's move on to proteins. So proteins are a bit different. They're broken down by proteases. So these are the enzymes that act on proteins. There are different types of proteases. And their differences basically are based upon where along that peptide bond this enzyme cleaves. So endopeptidases are going to cleave within the interior of the peptide bond, right? So not towards the exterior, not towards the peripheral end, but they're going to cleave along the middle parts of the peptide bond. Exopeptidases are going to be the opposite. They will cleave towards the end, the peripheral ends of this peptide bond. We also have zymogens, and there are different types of zymogens, but these are the storage form, like the inactive storage of these proteases, and they're stored in zymogen granules. Okay, so zymogen granules we see extensively in the pancreas. And basically we see these little droplets with lots of little vesicles inside of it, and those are the proteins that are sitting in these granules waiting to be released. They can be released by exocytosis, right? We talked about that process where these enzymes are packaged into a vesicle and then released on the surface of the cell. And this happens by proteolysis, right? This is activated by proteolysis, which is the breakdown of that protein. Now, the digestion of proteins begins in the stomach, unlike what we saw with carbohydrates. And we have the active form, pepsinogen, the active form of the hormone pepsinogen. That's going to be transferred to pepsin. It's going to be activated. And we talked about this. The presence of acid, that acidic environment in the stomach, is what activates this pepsinogen, right? Remember that suffix gen into its active form, pepsin, and then it can then act on the protein, right? That complex peptide and break it down into smaller amino acids. Now, pepsin also is going to activate chief cells to secrete that pepsinogen and then activated by hydrochloric acid. And the hydrochloric acid, in order to activate the pepsinogen, what it's doing is it's cleaving it. Right? So pepsinogen is a longer protein or a longer enzyme, and cleaving off a part of it is what activates it, and that happens in the presence of hydrochloric acid. And just to remind ourselves, the cells that secrete this acid are called parietal cells, right? Parietal cells. What was the other substance we mentioned parietal cells secrete? We mentioned the second substance released by parietal cells. So that was intrinsic factor, and that is responsible for the breakdown or the absorption of vitamin B12, right? So parietal cells are secreting acid and intrinsic factor. Chief cells are secreting pepsin. All right, so we continue on with the breakdown of starch in the stomach. And we have different types of proteases here. We have trypsin, chymotrypsin, carboxypeptidase. And again, the only difference between these different proteases is where along that polypeptide they cleave. They are going to move across the brush border. And so we have brush border proteases along the small intestines. Examples of those are aminopeptidase and enterokinase. So different types of peptidases, we don't have to get into the nitty gritty of the details, but just know that they cleave at different points along those peptides. All right, so once we've cleaved those amino acids into smaller building blocks, we can absorb them as amino acids. Right? We can either absorb them as full peptides, dipeptides, and tripeptides, or as amino acids. For them to be absorbed as amino acids, again, similar scenario, they must cross the apical surface of those epithelial cells, and they do so by a secondary active transport or facilitated diffusion. We just looked at an example of secondary active transport. And then they move across the basolateral surface of that cell by a facilitated diffusion, right? Meaning that they need some sort of carrier, and this does not require energy. This is passive. If they are full peptides, dipeptides, or tripeptides, they can still be absorbed, but the process is a little bit different. They move across the apical membrane by active transport, right? So this requires pumping right into the cell, and this does not happen with any other ion. And then they can move across the basolateral surface again by facilitated diffusion. What we want to remember here is that they must be broken down into amino acids. So once inside the cell, those peptides can be further broken down to amino acids and then absorbed into the blood. We cannot absorb full peptides into the blood, but we can move full peptides into the cell. All right, and just reminding ourselves of those types of movement here. So the top again is active transport, primary. The bottom is going to be secondary active transport. All right, moving on to lipids. Lipids are very different. They're very unique. We know that lipids are nonpolar, and that means simply that they do not play nicely with water. Okay, so lipids are a special case in terms of the way that they are absorbed and the way that they're moved around the body. So because they're nonpolar, they have to be aggregated to these big droplets. So when you eat a fatty meal or you eat fatty in your diet, it's absorbed and it's in a form of a fat droplet. So I mean, it's just congregating or aggregating into this big ball. And then that has to be acted on. That has to be further digested. So lipases are the enzymes that break down lipids, and they're secreted from the pancreas. And lipases can only interact with the exterior surfaces of this fat droplet. If you have a large fat droplet, lipases are only able to interact with the molecules that are facing the exterior surface of this droplet. What does that mean for us? Right? We want to get this big droplet into a smaller droplet in order for that lipase to interact with all parts of the droplet and break down all those fats evenly. And this is where bile salts come in. All right, we talked about bile. Bile salts stored in the gallbladder, secreted from the liver, right, the acinine cells of the liver. And biles help to break that big fat droplet into smaller fat droplets. This process is called emulsification, and this is why we secrete bile. This is why bile is secreted in response to fatty meals, because it's directly breaking down those fat droplets in order for them to easier be absorbed. So if you look at bile salts, they're an amphipathic molecule, and amphipathic is a term that we talked about last semester, right? Amphipathic meaning that there are polar regions to this molecule and there are non-polar regions to this molecule. What else is amphipathic in our body? What else is amphipathic in our body? What else is amphipathic? It has polar and non-polar regions. The lipid bilayer. So the membrane, the cell membrane, the lipid bilayer that makes up every single cell is also very similar structure. It's amphipathic. There are polar regions facing the aqueous solutions on either side of the cell, and the non-polar regions that are facing the interior, right? And so having these bile salts is crucial to the digestion and breakdown of fats. Continue on here. So if we digest fats, some of those fatty acids and monoglycerides can be absorbed directly, right? If you break them down to small enough components. I think about this large fat globule at the top of the cell. We can break some of this down into smaller components that can be more easier to absorb by those lipases. Others have to be formed into what's called a micelle. We talked about a micelle. A micelle is this droplet that has the aqueous parts of the molecule facing the exterior and the fat sort of clustered inside, that non-polar region. And so micelles are an important structure in the absorption of fatty acids and monoglycerides. And they help to be absorbed using those lipases. So let's talk about how fat moves across the epithelial cell, how it's absorbed. So free fatty acids and monoglycerides can move freely by a simple diffusion. They do not need any sort of transporter to move into the cell. Once they're inside the cell, they are then repackaged, right? They travel to the Golgi apparatus. Right, so we have this large fat droplet here, which is made of triglycerides. So those are complex fatty molecules. They're broken down into their smaller components, fatty acids and monoglycerides, or micelles. So this is either or. These molecules will then be packaged into what's called a chylomicron. This happens in the Golgi apparatus. So the Golgi apparatus is like the post office of a cell. We talked about those organelles within the cell. And in the Golgi apparatus, the fatty acids or monoglycerides are packaged very nicely into chylomicrons where they can move around in an aqueous solution very easily, right? So just to look at that example here, we have the lumen of the GI. We have these free fatty acids or monoglycerides. They can freely move into the cell. They're repackaged in the Golgi apparatus into a chylomicron. So again, a chylomicron is a structure that allows these fatty molecules to play nicely with water. Once they're repackaged into this chylomicron, they are exocytosed across into the capillary, and from the capillary, they can either move into the blood. So there are some chylomicrons in the blood, and this is where cholesterol and cholesterol levels come into play, or more intentionally, they can move into the lacteals, and this gives them access to the lymphatic system. Right, so we talked about the lacteal yesterday. It's that structure right in the middle of the villi, specifically in those intestinal cells, those enterocytes, and it's responsible for the absorption of fats, and this is how it happens. So from the lacteal, fats will then move around within our lymphatic vessels and the lymphatic circulation and be absorbed that way. All right, so here we have again, these bile salts secreted by the liver are responsible for emulsifying those fats. And then what we see here is that once these bile salts make it to the ileum, so remember the gallbladder has that duct that opens into the duodenum, which is the first part of the intestine. At the end of the intestine, so in the ileum, these bile salts are reabsorbed into the capillaries, reabsorbed into the blood. They enter the portal circulation. Remember we talked about the portal circulation that recycles that blood, sends all that blood from the GI system into the liver to be detoxified. Well, what happens is these bile salts hitch a ride on this portal system. They enter the portal system, head to the liver, they are recycled, and we can make new bile salts. So the take-home message here is we do not just lose those bile salts in the feces. We don't just remove them from the body, right? We're going to repurpose them by reabsorbing them at the end of the small intestine, so in the ileum, repurposing them in the portal system, and making new bile salts. Okay. All right, so let's talk about the absorption of vitamins. Now, we typically know that there are two types of vitamins, fat-soluble vitamins and water-soluble vitamins. Fat-solubles are A, D, E, and K. They are absorbed with the absorption of fat. So into those micelles are packaged as chylomicrons, and then entering the lymphatic system via the lacteal. Water-soluble vitamins, on the other hand, they require transporters. Why do they require transporters? Why do water-soluble vitamins require transporters? Isn't it small enough to just move across the lipid bilayer? No, so we know that soluble items, soluble molecules such as water-soluble vitamins cannot move across that non-polar region of the lipid bilayer. So they require special transporters. Vitamin B12 is sort of a special case. It needs to be bound to intrinsic factor in order to be absorbed, right? We talked about intrinsic factor, which is released by the colloidal cells of the extragrams. Questions? Any questions? All right, let's talk about the absorption of some minerals. So sodium is one of the most important minerals in the body, and it's absorbed with water. So it easily moves across the epithelial cells, and we know that water follows sodium. So there's that water drag with the movement of sodium, and we saw that extensively in the kidney. It's specifically absorbed in the jejunum, ileum, and in the colon. And during these areas of these parts of the intestines, rather, we also see water moving. We also see the absorption of water, which is following that sodium. Chloride passively follows sodium. We talked about this. Chloride loves to hitch a ride with sodium because of that opposite charge, and it moves passively along with the absorption of sodium. Potassium is passively absorbed as well, and it's secreted at different areas in the lumen. Right? Potassium is one of those ions that we can secrete. So you see this in the kidneys as well in order to maintain that balance. And we also talked about the relationship with hydrogen ions and potassium, but they have that symbiotic relationship where they follow each other. Moving on to absorption of bicarbonate. This happens specifically in the jejunum, so the second part of the small intestines. And these bicarbonate ions are passively absorbed, meaning they don't require any energy, they don't require any ATP. In the ileum and the colon, we see bicarbonate being absorbed in an exchange for chloride ions. So in the jejunum, they move freely. In the ileum and the colon, they're being exchanged for chloride. And this relationship, just to point out here, this relationship between chloride in the large intestines plays a significant role in the disease cholera. If you've ever heard of cholera, the movement of chloride and sodium in the colon, and that channel that's disrupted by the cholera bacteria is where that diarrhea comes about in the colon. And calcium is actively absorbed in the duodenum and jejunum, so the first bit of the small intestine, and it binds to those calcium binding proteins and are transported into the epithelial cell. They can move across the basolateral membrane to the bottom of that cell by actively being pumped by calcium pumps. Right, so it moves into the brush border via proteins and across the basolateral surface via calcium pumps. Ion is sort of a special case. Ion has to be bound to transferrin to be secreted. And it's done so by enterocytes. It moves in the intestines. Transferrin binds onto this ion, and this transferrin ion complex together binds to a receptor on the cell. So ion cannot just go up to this receptor and bind. It's not going to get in. It has to be bound to transferrin to move around and to bind to that receptor. Once ion and transferrin, that complex, once they bind to that receptor, we have what's called receptor-mediated endocytosis, which is where a vesicle opens up, and that molecule, that complex together, is engulfed within the cell. All right, now in terms of the storage of ions, some of it is stored as ferritin, and some of it is freely moving around the blood, also bound to transferrin. Keep that in mind. Ion cannot move around the blood or enter the cell on its own. It must be bound to transferrin. Hence the term transferrin, right? That suffix ferrin is referring to the ion component. And lastly, water very easily moves right across the membrane. It's passive. This happens usually according to gradient, so high to low concentration, depending on the amount of solute on either side of that membrane. Okay, and you also want to remember here that water follows sodium. So if you have sodium moving in one direction, water will likely follow.